On July 21st, 1942, a thermometer in Miami read 100 degrees Fahrenheit. In the 130 years since anyone started keeping records there, it has never happened again. Not once. Miami is one of the hardest places in America to push to 100 degrees, and this morning the National Weather Service put the forecast high at 99, with a 1 in 10 chance of touching the number that has stood alone since the summer Franklin Roosevelt was president. But the record is not the interesting part. The interesting part is why it stood for 84 years, because this city has 3 separate natural defences against extreme heat, all of them powered by the same ocean, and right now at least 2 of them have stopped working. The question is what changed in the water. If that hooks you the way it hooked me, hit the like button and subscribe to the Skylab, because the thing driving this has not peaked yet and we will be following it for months. Drop a comment and tell me where you're watching from, and whether the heat this summer has been worse where you live than you can remember it being. Now, let's get into it. Part 1. 1 degree, 84 years. The forecast high for Miami today is 99 degrees. That is the number the National Weather Service office in Miami put out for the official climate station at Miami International Airport. And attached to it is a small, quiet probability that most people scrolling past a weather app will never see. Roughly a 1 in 10 chance of touching 100. Not a headline. Not a warning in bold red type. Just a forecaster's honest acknowledgement that the atmosphere over South Florida today is close enough to a line that the line might get crossed. You need to understand what that line is, because on its own, 99 degrees sounds like an ordinary bad summer day. Sounds like Texas in July. Sounds like a Tuesday in Oklahoma. In Miami, it is nothing of the kind. Miami has reached 100 degrees exactly once. Not once this decade, not once this century. Once. On July 21st, 1942, the official thermometer at the Miami Climate Station registered 100 degrees Fahrenheit, and in the entire instrumental record from 1896 through the end of 2024, it has never happened again. Not during the heat of 1998. Not during the summer of 2010. Not during 2023, when the city ran 46 consecutive days with an afternoon heat index above 100 and the National Weather Service issued excessive heat warnings for Miami for the first time in its history. Through every one of those events, the all-time record held 84 years, 1 afternoon. And today, a professional forecaster looked at the data and wrote down a 1 in 10 chance. The alert that went out for South Florida this morning runs from noon until 7 in the evening, and it describes dangerous heat with no rain and no breeze anywhere in the forecast. Feels like temperatures are expected to climb as high as 112 degrees. The heat index is expected to reach the danger range by early afternoon and peak somewhere near 110 degrees between 3 and 5, staying elevated into the evening before it eases after sunset. That is not the air temperature. That is what the air temperature does to a human being when the air is carrying as much water as the air over Miami is carrying right now. We will come back to that gap, because that gap is where this entire story actually lives. Here is the thing I want to put in front of you before anything else, because it reframes everything that follows. The remarkable number today is not 99, it is the 10%. Think about what a probability actually means. Climatologically, the odds of any given day in Miami reaching 100 degrees are somewhere on the order of 1 in tens of thousands. That is what happens when you have one occurrence spread across 130 years of daily observations. It is a number so small that it functions, for practical purposes, as 0. Nobody in Miami plans around the possibility of a 100-degree day, because in 130 years of records, exactly one person ever had to. So when a forecaster who knows that record perfectly well sits down with today's model guidance and writes 10%, they have not made a small adjustment. They have taken something that was effectively impossible and moved it into the range of things that might happen this afternoon. The departure from the baseline is not incremental. It is several orders of magnitude, and this is not the first record to fall in this particular stretch of weather. During this same heat episode, Miami has already broken a daily record with a 96-degree reading that displaced a 95-degree record standing since 1999. It tied another daily record at 94 degrees, on a day when the heat index ran from 106 in Miami proper, out to 113 at Kendall Lakes, which is barely 20 minutes inland. A 98-degree reading in the city's history is noted as tied for the second highest temperature ever recorded at that station. Second highest, 98. And the top of the list, alone, unaccompanied standing by itself since the summer Franklin Roosevelt was president, is 100. That gap between second place and first place is not a gap in the weather. It is a gap in the physics, and it is the reason this video exists. Because here is the fact that almost nobody outside of meteorology carries around in their head. Miami is one of the hardest places in the continental United States to push to 100 degrees. Not one of the coolest. Miami is brutally, oppressively hot. It is one of the hardest to push to that specific number, and those are completely different statements. Phoenix reaching 100 degrees requires heat, that is all. Dry air, strong sun, a warm air mass, and the thermometer climbs. Phoenix has already recorded 28 days at or above 110 degrees this year, and it will record more before September is finished. The desert does not need anything unusual to happen, it just needs summer. Miami reaching 100 degrees requires heat, and then it requires something else entirely. It requires the simultaneous failure of 3 separate systems that have been holding the city's temperature down for as long as anyone has been measuring it. 3 breaks. That is how I want you to think about this. A coastal, subtropical city sitting on a narrow strip of land between the Atlantic and the Gulf of Mexico has 3 independent mechanisms working against extreme air temperature, and every single one of them is powered by the water surrounding it. The first is the humidity itself. Wet air resists heating in a way that dry air does not, and we're going to walk through exactly why. Because the mechanism is counterintuitive, and it is the single most misunderstood thing about heat in the American Southeast. The second is the sea breeze. Every afternoon, reliably, a circulation develops between the land and the water, and it pushes marine air inland across the city. It is the reason a South Florida afternoon has a wind in it. The third is the storms. Those sea breezes, advancing from both coasts of a narrow peninsula, collide somewhere in the middle, and where they collide, they build thunderstorms. Those storms shade the surface and cool it with rain exactly when the sun is at its strongest. Humidity, wind, storms, 3 breaks, all of them running off the same ocean. Today, at least 2 of them are not working, and by the time we're finished, I am going to make the case that the reason they are not working is not really about the weather at all. Because you cannot look at Miami alone today. This city is a single station inside something much larger. Right now, across the central, southern and eastern United States, roughly 30 million Americans are under what NOAA classifies as extreme heat risk, and another 50 million are under major heat risk. 80 million people, close to a quarter of the country's population, all sitting underneath one atmospheric structure. Heat indices between 105 and 115 degrees are being recorded from the Gulf Coast through the southern plains and out into the desert southwest. At least 9 daily maximum temperature records were expected to fall over the preceding weekend, with dozens more high and low records challenged through the week. And the Weather Prediction Center flagged something about the structure itself that I want you to hold on to because we will spend an entire section on it later. The high-pressure ridge producing all of this was forecast to break monthly records for the intensity of its high pressure. Not a record temperature, a record ridge. So the question in front of us is not really whether a thermometer at an airport in South Florida shows a 99 or a 100 this afternoon. That is the headline, and the headline is the smallest part of it. The real question is what happened to a set of natural defences that have held a threshold intact through every heat event of the last 84 years, and why they all appear to have gone offline at the same time. The number that matters today is not on any thermometer. It is the number of breaks that stopped working. Part 2. The only 100 Miami has ever recorded. July 21st, 1942. That is the entire list. If you ask the National Weather Service for every date on which the official Miami climate station reached 100 degrees Fahrenheit, you would receive a single line of text, and the ink would run out almost immediately. The continuous instrumental record for Miami begins in 1896. That gives us something in the neighbourhood of 47,000 days of observations, 47,000 afternoons of a thermometer being read, logged and archived, through the Depression, through 2 world wars, through the post-war boom and the air conditioning revolution that made modern South Florida possible in the first place. 47,000 chances, 1 qualifying afternoon. I want to be careful here. because there is a statistical trap sitting in the middle of this, and I would rather walk you around it than pretend it is not there. One event is not a sample. You cannot look at a single occurrence across 130 years and calculate a meaningful return period from it. Saying Miami hits 100 degrees once every 130 years sounds precise, and it is very nearly meaningless, because you are estimating a frequency from a sample size of 1. The honest statement is different and I think more interesting. The honest statement is that Miami's summer maximum temperatures have a hard right edge somewhere around 100 degrees, and nobody actually knows whether that edge is a physical ceiling or a sampling artifact. Is there something in the physics of a saturated subtropical marine air mass that makes 100 degrees genuinely difficult to reach, a wall the atmosphere runs into? Or is it simply that in 130 years of rolling the dice, the numbers came up right one time and could have come up right 5 times with slightly different luck? That question has been academic for 84 years, because nothing has come close enough to test it. Today, something is close enough to test it. Now, whenever a record like this comes up in conversation, someone reaches for the obvious argument, and I want to deal with it now rather than at the end, because it is a reasonable argument and it deserves a real answer. The argument goes like this. If the hottest day in Miami's history happened in 1942, and nothing has beaten it in 84 years of supposed warming, does that not suggest that nothing much has actually changed? It is a fair question, and it uses a real number, which already puts it ahead of most objections. Here is where it breaks down. A daily record measures one afternoon. It measures the single most extreme value in a very long series, and single extreme values are noisy by their nature. They depend on a specific alignment of conditions on a specific day, and that alignment can happen early in a record or late in a record purely by chance. A climate is not a peak. A climate is a distribution, and distributions have many more properties than their maximum value. So if you want to know whether the climate of South Florida has moved, do not look at the highest number in the archive. Look at everything else in the archive. Look at the heat index records, which fell by the dozen in 2023. Look at streak records, which we will get into in detail. Look at overnight minimum temperatures, which are quietly the most important measurement in this entire story. Look at sea surface temperatures in the water surrounding the city, which have been running at record daily highs. Every one of those metrics has moved substantially. The daytime air temperature peak is the single metric that has barely budged. And that is not a rebuttal, that is a clue. Because the reason the daytime peak has not moved is the same reason the danger has increased, and understanding that connection is the whole point of what we are doing here. Miami's geography is the starting point for all of it. Look at a map of South Florida, and what you see is not really land. It is a sandbar with cities on it. The peninsula is narrow, the Atlantic sits immediately east, the Gulf of Mexico sits west, the Everglades sit in the middle at almost no elevation, and Florida Bay wraps the southern end. There is essentially nowhere in South Florida that is far from water, and there is nowhere at all that is high above it. That matters because it means the air over Miami is almost never continental air. It is marine air. It has spent time over a warm ocean surface before it arrives, and it carries the fingerprint of that ocean in the form of water vapor. On a typical August afternoon in Miami, the dew point sits in the mid-70s, which is a level of atmospheric moisture that most of the country experiences only in the worst days of a Midwestern heat wave. That moisture is the first break, and it is the strangest of the three, because it works against the very thing that makes people afraid of it. The wetter the air, the harder it is for the air temperature to climb. I know that sounds backwards. Everyone who has stepped outside in Miami in August knows that humid heat is worse than dry heat. And it is worse. That is exactly right. And it is a completely separate question from what the thermometer reads. The mechanism has to do with where the sun's energy goes when it arrives at the surface. Every hour of daylight delivers a budget of energy to the ground, and that budget gets split. Some of it raises the temperature of the ground and the air above it. Some of it evaporates water. Those are two different destinations for the same energy, and the split between them determines what your thermometer reads. In the Sonoran Desert, there is no water at the surface to evaporate. Essentially, the entire budget goes into raising temperature, which is why Phoenix runs at 110 and 11 degrees this week, while sitting under the very same pattern that is over Miami. In South Florida, there is water everywhere. There is water in the soil, water in the Everglades, water in the canals, water in the bay, and above all there is water already in the air, and the sun spends an enormous fraction of its daily budget moving that water around instead of heating it. The energy does not vanish. That is critical. It is still there. It has simply been converted into a form your thermometer cannot see, and your body absolutely can. So when Miami sits at 99 degrees with a heat index near 110, the 11-degree gap between those two numbers is the energy the thermometer missed. It is stored in the water vapor, and your body, which cools itself by evaporating sweat into that same air, has to contend with all of it. That is the first break. It is still working today. It is holding the number down as we speak, which is exactly why the number climbing to 99 anyway should make the hair on your arm stand up, because the brake is on and the car is still accelerating. To see what actually failed, we have to look at the second one, and the second brake is not a property of the air, it is a machine. Part 3. The first brake. Water in the air. Let me put a contradiction in front of you and then take it apart. The most humid major city in the continental United States is also one of the hardest places in the continental United States to push past 95 degrees. Those two facts sound like they should belong to different cities. They are the same fact seen from two sides. To understand why, we need to talk about what heat actually is, because in everyday language we use one word for two different things and the confusion causes real trouble. There is heat as energy and there is temperature as a measurement. They are not the same. Temperature tells you how fast molecules are moving, energy content tells you how much is in there in total, and a substantial amount of energy can be present in a form that does not move molecules faster at all. It can be locked up in a phase change, in the difference between liquid water and water vapor. Turning liquid water into vapor takes an enormous amount of energy, far more than heating the same water by a few degrees. That energy does not disappear when the water evaporates. It travels with the vapor, invisible to a thermometer, waiting to be released again the moment that vapor condenses back into liquid. Meteorologists call it latent heat, and it is the single largest energy transport mechanism in the atmosphere. It is what powers hurricanes. It is what powers thunderstorms. It is what makes the tropics the engine of the global circulation. Now apply that to a Miami afternoon. The sun comes up over a landscape saturated with water and an air mass already carrying a heavy vapor load. As the surface heats, evaporation accelerates. Every gram of water that leaves the surface as vapor takes a substantial packet of energy with it, and that energy is subtracted from the pool available to raise the air temperature. The result is a thermal system with an enormous buffer. You can pour hours of intense August sunlight into it and get a stubbornly modest rise in air temperature, because the system keeps converting the input into vapor rather than into motion. The desert has no buffer at all. Sun arrives, ground heats, air heats, temperature climbs, and there is nothing to slow it down. This is why the hottest air temperatures ever recorded on Earth all come from deserts, and none of them come from rainforests, despite rainforests receiving more solar energy at the top of the atmosphere. The rainforest is doing something with the energy. The desert has nothing to do with it but get hot. So South Florida makes a trade, and it is worth stating the terms of that trade explicitly, because the terms have changed. Miami accepts a lower peak air temperature in exchange for carrying an enormous moisture load. For most of the last century that was a good trade. It kept the thermometer down, it kept the record intact, and it made the city livable in a way that a comparable latitude in the interior would not have been. Brian McNulty, a researcher at the University of Miami who maintains a long-running climatology of the city's heat index and dew point, has made the analytical point about this better than anyone. His argument is that the heat index is the more revealing metric because of how it responds to small changes. Nudge the temperature up a little, nudge the dew point up a little. Neither of those changes looks dramatic on its own. But because the heat index depends on both together, and because the relationship is not linear, those two modest nudges produce a large jump in the heat index. Sit with that for a second, because it explains the entire shape of this story. If you warm the region slightly and moisten it slightly, the daytime maximum temperature moves a little. It might not move enough to break an 84-year-old record. Meanwhile, the number that describes what the air is doing to human beings moves a great deal, and the record books track the first number, because air temperature is what stations have measured continuously since the 1890s, and it is what the archive is built around. Which means the official record of Miami's climate systematically undercounts the change that has actually occurred there. Not through error, not through manipulation, but through measuring the wrong quantity for the specific place. The archive is honest. It is just answering a different question than the one we need answered. You can see this play out directly in today's numbers. The air temperature is forecast at 99 degrees. The heat index is forecast near 110. 11 degrees of separation, and all 11 of them are made of water vapour. 11 degrees is not a rounding difference. It is the difference between a hot day and a day where the National Weather Service tells people not to be outside. And here is what makes it worse rather than better. The heat index scale is not linear in the direction of comfort. As dew points climb into the mid and upper 70s, the same 1 degree increase in air temperature produces a larger and larger jump in apparent temperature. The curve steepens. The air gets more dangerous faster than the thermometer suggests it should. There is a second consequence of the humidity break that almost nobody discusses, and it concerns the night rather than the day. Water vapour is a greenhouse gas. It is, in fact, the most abundant greenhouse gas in the atmosphere. Its presence in the air column directly reduces the rate at which the surface can radiate heat away to space after sunset. In dry desert air, the ground sheds heat rapidly overnight, which is why deserts that hit 115 degrees in the afternoon can drop 40 degrees by dawn. In saturated marine air, the surface radiates into a blanket and the temperature barely moves. So the first break gives with one hand and takes with the other. It suppresses the daytime peak, and it props up the nighttime floor. It holds the record intact and removes the recovery period. If you were designing a climate to produce reassuring record books and dangerous conditions simultaneously, you would design this one. There is a way to measure this split directly, and it has a name. The ratio of energy going into heating the air versus energy going into evaporating water is called the Bowen ratio, and it is one of the most useful numbers in surface meteorology because it tells you what kind of place you are standing in without you having to look around. Over a desert, the Bowen ratio is high. Most of the energy heats the air, very little evaporates anything, and the surface behaves like a hot plate. Over a swamp, a wetland, or a shallow warm sea, the ratio inverts. The overwhelming majority of the energy goes into vapour, and the air temperature climbs slowly and stops early. South Florida is one of the largest low-ratio surfaces in North America, and the reason is sitting immediately west of Miami. The Everglades is a sheet of shallow water moving imperceptibly south across a limestone shelf, covered in vegetation that transpires constantly, and it functions as an evaporative machine roughly the size of a small state. Air that crosses it does not arrive in the city dry. At the canals, the bay, the porous limestone that holds groundwater within a few feet of the surface almost everywhere, and you have a landscape that is physically incapable of behaving like a desert, no matter how hard the sun works. That is why the record has been so hard to break. It is not luck, and it is not an accident of station sighting. It is a genuine physical property of the surface the city was built on. And that brings us to the thing I keep circling, which is that the first break is still functioning today. Nothing has broken about the physics of latent heat. The air over Miami this afternoon is still absorbing an enormous fraction of the incoming solar budget and converting it to vapour rather than temperature. That break is fully engaged. The thermometer is reading 99 anyway. That is what should worry you, not a hot day. A hot day with the primary suppression mechanism fully operational, which means whatever is happening today is happening in spite of the buffer, not because the buffer failed. To find the failure, you have to look for the break that is mechanical rather than thermodynamic, because humidity is a property of the air, and a property cannot break, but a circulation can stall. Part 4. The second break, the wind. Off the water. If you have ever spent a summer day in South Florida, you know the rhythm without having to be told. Morning is still. The air is heavy and quiet, and the heat builds fast. And then somewhere in the late morning or early afternoon, something changes. A wind arrives from the east, off the water, and it does not feel dramatic, but it is unmistakable. The flags shift. The temperature curve, which had been climbing steadily, bends. That wind is not weather in the ordinary sense. It is a machine, and it runs every day, and it runs for a specific physical reason. The mechanism is called a sea breeze circulation, and it exists because land and water respond to sunlight completely differently. Water has an extraordinarily high heat capacity, and it mixes vertically, so solar energy absorbed by the ocean gets distributed through a deep layer, and the surface temperature barely changes over the course of a day. Land has a low heat capacity and does not mix, so all of the energy stays in the top few centimetres and the surface temperature climbs fast. By late morning, the land is significantly warmer than the water beside it. Warm air over the land expands and rises. That rising creates a slight deficit of mass near the surface over land, which lowers the surface pressure slightly relative to the water. The atmosphere responds to that pressure difference in the only way it can. Air flows from the higher pressure over the water toward the lower pressure over the land. That flow is the sea breeze, cool marine air pushing inland at the surface, warm air rising over the land, a return flow moving back seaward at altitude, and gentle sinking motion out over the water to close the loop. A complete circulation cell, thermally direct, powered entirely by the temperature difference between the city and the ocean beside it. Everything about that description hangs on one phrase, and I want you to notice it now, because it becomes the pivot of this entire video. Powered entirely by the temperature difference between the city and the ocean beside it. Miami's official climate station sits at Miami International Airport, close enough to the coast that when the sea breeze fires, the marine air reaches it early in the heating cycle. That matters enormously for the record. The station is not in the interior where the sea breeze arrives late and weakened. It is positioned where the break grips hardest. Now factor in the shape of the peninsula. Florida is narrow, and it has two coasts, which means it develops two sea breezes simultaneously. One pushes west off the Atlantic, one pushes east off the Gulf. They advance toward each other through the day, and they meet somewhere in the interior. On a typical summer day, there is essentially nowhere in South Florida that escapes marine influence entirely, because the marine air is arriving from both directions. That is the second break. And unlike the first one, it has moving parts, and things with moving parts can fail. There are two distinct ways to break a sea breeze, and it is worth separating them carefully because they lead to different conclusions. The first failure mode is the pressure pattern. A sea breeze is a weak circulation. It is a local, shallow feature driven by a modest pressure gradient, and it can be overwhelmed by a stronger large-scale flow. When a powerful high-pressure ridge parks overhead, it generates its own low-level wind field, and depending on the orientation of that field relative to the coast, it can slow the onshore push, hold it offshore, or reverse it into an offshore flow that brings hot air out from over the interior instead of cool air in from over the water. That is the failure mode operating today, and the forecast discussion names it precisely. There is a west wind over South Florida this afternoon, and a west wind is exactly the wrong wind. It is blowing from the interior of the peninsula toward the Atlantic coast, which means it is running directly against the direction the sea breeze needs to travel. The onshore push cannot establish itself against it. So the forecast for South Florida this afternoon says explicitly that there is no ocean breeze developing along the coast. Not a light breeze. None. On a peninsula that generates an onshore wind essentially every summer afternoon of its existence, the machine is not running, and the reason is a wind blowing the wrong way across the Everglades. The second failure mode is subtler and much more important, and it does not require any pressure pattern at all. Remember what powers the circulation. The temperature difference between the land and the water. Not the temperature of the land, the difference. So consider what happens if you warm the water. The land still heats fast in the morning, but it is now heating relative to a warmer starting point offshore. The contrast between them narrows. A narrower contrast means a weaker pressure gradient, and a weaker pressure gradient means a weaker circulation. The sea breeze still forms, but it forms later, it moves slower, it penetrates less far inland, and crucially, the air it carries is warmer than it used to be. At some point along that spectrum, a sea breeze stops being a cooling mechanism in any functional sense. It is still a wind. It is still air moving from the water toward the land. It is simply no longer bringing anything cooler than what is already there. And that raises a question I am going to leave hanging for now, because it takes the entire third act of this story to answer properly. How warm is the water? The seasonal average for Gulf of Mexico water temperature in August runs between 84 and 88 degrees Fahrenheit, with local values reaching as high as 92. Think about what those numbers mean for a marine air mass. Air that has been sitting over a 90-degree ocean surface, picking up moisture and heat from it, is not a cooling agent when it arrives over a city. It is a delivery vehicle for warmth and moisture, and there is a historical marker for how far this can go that I want to plant here, because we will return to it. In July of 2023, a sensor in Manatee Bay near Everglades National Park recorded a water temperature of 101.1 degrees Fahrenheit at 6 in the evening. That reading became a candidate for the warmest seawater ever measured anywhere on Earth. Its record status remains contested, and legitimately so because Manatee Bay is shallow, murky and restricted, and a shallow enclosed bay is not the open ocean. But the sensor was not broken. The reading exists, and whatever you want to call it, water at 101 degrees is not going to cool a city. So step back and look at where we are. 3 breaks. The first, humidity, is thermodynamic, and it is still working, and the temperature is at 99 anyway. The second, the sea breeze, is mechanical, and today it is not running, either because the pressure pattern has overwhelmed it, or because the contrast that drives it has weakened, or most likely both at once. That leaves the third break. And the third break is the loudest, most visible, most unmistakable feature of a South Florida summer afternoon. It builds towers 30,000 feet into the sky. It turns the light green. It drops the temperature 15 degrees in 10 minutes and floods the streets, and then clears out by dinner. Today, it simply did not happen. And the reason it did not happen is sitting 40,000 feet above the city, and it is at a record value. Part 5. The third break. The storms that didn't build. There is no rain in today's forecast for Miami. None. 0% across the entire afternoon. On a normal day in the middle of August in South Florida, that sentence would be strange enough to be worth commenting on by itself. August is the wettest stretch of the year in Miami. The climatological expectation for a mid-August afternoon is not a chance of storms. It is storms. The sky builds, the towers go up, the light changes, and somewhere between 2 and 6 in the afternoon the bottom falls out. That daily cycle is the third break, and it is the most powerful of the 3 by a wide margin. Here is how it is built. The 2 sea breezes we just talked about, one advancing west off the Atlantic and one advancing east off the Gulf, are both pushing air toward the interior of the peninsula. When 2 air masses move toward each other, the air between them has nowhere to go but up. That forced ascent is called convergence, and along the line where the 2 sea breezes meet, the atmosphere is being physically shoved upward all afternoon. Now add the ingredient South Florida has in unlimited supply: moisture. When you lift a saturated air parcel, it cools, the vapor inside it condenses, and condensation releases every bit of that latent heat we discussed earlier back into the parcel. The released heat makes the parcel warmer than its surroundings, which makes it more buoyant, which makes it rise faster, which condenses more vapor, which releases more heat. The process feeds itself. That is a thunderstorm, and in a moisture-rich subtropical environment with a reliable daily lifting mechanism, it is close to inevitable. The timing is what makes it a break rather than just weather. Convergence peaks when the sea breezes are strongest, and the sea breezes are strongest when the land is hottest, which is the middle of the afternoon. So the storms build precisely when the temperature curve is trying to make its final push toward the daily maximum. And they attack that push in 2 separate ways. First, the anvil and the tower shade the surface, which cuts the incoming solar energy at the exact hour it would be greatest. Second, rain falling through the storm cools the air by evaporation, and that cooled air, being denser, sinks and spreads out along the ground as an outflow boundary. It arrives as a gust of air that can be 15 or 20 degrees cooler than what it replaces, and it can arrive several miles from where the rain is actually falling. Shade plus outflow is why the Miami temperature curve so often has a flat top with a sharp cliff on the right side. The city does not get hotter through the late afternoon. It gets cut off. If you want proof of how decisive this mechanism is, the record book supplies it. In 2023, Miami ran 46 consecutive days with an afternoon heat index above 100 degrees, which was the longest such streak in the city's history by a very wide margin. That streak ended on July 27th. It did not end because a cold front arrived, or because the season turned, or because the pattern relaxed. It ended because heavy rain fell and capped the heat index at 98. One storm. That is what it took to break the longest heat streak Miami has ever recorded. That is the power of the third break, and it is why its absence is the loudest silence in today's forecast. So what turns it off? The answer is subsidence, and subsidence is the signature of a strong upper-level ridge. When a large area of high pressure builds aloft, the air within it sinks. As air descends, it is compressed by the increasing pressure around it, and compression warms it. This has nothing to do with sunlight or the surface. It is purely mechanical heating, and it happens throughout the descending layer. Two things follow from that. First, the descending air warms, which means that somewhere in the middle levels of the atmosphere you develop a layer that is warmer than it has any right to be. A rising parcel from the surface climbs until it reaches air as warm as itself, and then it stops rising, because it is no longer buoyant. That warm layer is called a capping inversion, and it functions as a lid on the entire convective process. The parcel can be as moist as it likes. It cannot get through the lid. Second, descending air dries out. Its relative humidity falls as it warms, which erodes cloud from the top down. Under a strong ridge, the sky does not just fail to produce storms, it fails to produce clouds at all. And here is the compounding effect that makes a ridge so much more dangerous than it first appears. Removing the clouds removes the shade, which means the surface receives its full solar budget for the entire day with no interruption. So the ridge raises the temperature twice, once by warming the air directly through compression, and once by removing the thing that was cutting the sunlight off. Put all of that together, and you have today's situation stated precisely. The humidity brake is fully engaged and holding the number down. The sea breeze brake is not running. The convective brake is capped, 2 of 3 offline, and the thermometer is reading 99. Which brings us to the 1 degree, and I want to be honest about it rather than dramatic, because the honest version is more interesting. Physically, the difference between 99 and 100 is nothing. It is within the calibration tolerance of the instrument. There is no threshold in atmospheric physics at 100 degrees Fahrenheit. The number is an artifact of a temperature scale, invented in the 1720s by a man in Danzig who was trying to make his instruments reproducible. Archivally, the difference is everything. 100 is the number in the record book. 99 is a hot Tuesday nobody will remember by September. The record either falls or it does not, and today it comes down to rounding. Both of those things are true at once, and holding them together is the only way to see the story clearly. The significance of today is not that a specific value gets crossed. It is that the atmosphere over Miami got close enough that the crossing became a matter of a single degree, when for 84 years it was not a matter of anything at all. There is one more feature of the third break worth understanding, because it explains why its absence is felt across a much wider area than the storms themselves ever cover. Outflow boundaries travel. When rain-cooled air hits the ground and spreads out, it moves as a shallow density current, and it can run 20, 30, sometimes 50 miles from the parent storm before it dissipates. On an ordinary August afternoon, a cluster of storms over the Everglades sends a boundary racing east toward the coast, and neighborhoods that never saw a drop of rain still get the temperature drop. The brake is not applied where the storm is, it is applied across the whole peninsula. Which means that when convection is capped, the loss is not just the shade over one neighborhood, it is the removal of a cooling mechanism that normally covers everything from Homestead to Palm Beach on the same afternoon. Every part of South Florida is running today without a mechanism that ordinarily reaches all of it, and the 3 breaks are not 3 separate systems. That is the assumption I have been letting you carry, and it is wrong, and taking it apart is where this story stops being a weather report. Humidity comes from the water. The sea breeze is powered by the difference between the land and the water. The storms are built by sea breezes colliding. Every one of them draws on the same source. But before we go to the water, we have to go up. Because the thing capping the storms and stalling the breeze is a single structure in the atmosphere, and it is not merely strong. It is at a record value. Part 6. The Ridge. At 600 decameters. Forecasters looking at this pattern flagged something unusual, and it is the detail from this entire event that I suspect will still be cited years from now. The upper-level ridge responsible for this heat was expected to break monthly records for the intensity of its high pressure. Not a record temperature at a station, a record in the structure of the atmosphere itself. And once you understand what that means, the surface temperatures stop being the story and start being the receipt. So let us build the concept from the ground up, because upper-level ridges get mentioned constantly in weather coverage and almost never explained. Meteorologists do not usually map pressure at a fixed altitude. They do the reverse. They pick a pressure value, 500 millibars for example, which is roughly the level where half the mass of the atmosphere is below you and half is above, and then they map how high you have to climb to reach it. That height is called geopotential height, and it is measured in meters or in decameters, which are units of 10 meters. Why do it that way? Because height at a fixed pressure is a direct readout of the temperature of the air column underneath. Warm air expands and takes up more vertical space, so a warm column pushes that pressure surface higher. Cold air contracts, and the surface sits lower. A map of geopotential height is really a map of how warm the atmosphere is through its whole depth, and it removes all the noise that surface readings pick up from pavement, vegetation, elevation, and time of day. A ridge is a region where those heights bulge poleward. It means a deep, warm column. And this summer, the strongest ridge in the Northern Hemisphere in forecast guidance peaked near 5,998 geopotential meters on August 1st, over a point near 36 degrees north and 116 degrees west, which puts it in the desert country between Nevada and California. 5,998 meters. The round number meteorologists watch for is 600 decameters, which is 6,000 meters. Reaching it over North America is rare. This ridge came within 2 meters of it, which in practical terms means it got there. Alongside that, upper air thermal anomalies during this summer's ridge episodes have reached the 99th percentile. That phrasing deserves translation. It means that when you compare the temperature of the atmospheric column to every other observation in the historical record for that location and time of year, this one sits in the top 1%. Not a warm day. The warmest one day in 100. Now let us walk the mechanism from that height field down to a thermometer in Florida, because every step of it matters. A high geopotential height means a deep, warm, expanded column of air. That column is anticyclonic, meaning the air within it is diverging aloft and sinking through the middle levels. The sinking air is compressed and warms, which makes the column warmer still, which raises the heights further. Warmer column, higher heights, stronger subsidence, warmer column. It is a positive feedback loop, and once it establishes itself, it is extraordinarily difficult to dislodge. The subsidence produces the capping inversion we discussed, which kills convection, which clears the sky, which lets the full solar budget reach the surface, which heats the boundary layer, which feeds back into the warmth of the column. That is a second feedback loop stacked on top of the first one. This is why heat domes behave the way they do. They are not passive lids sitting over a region. They are self-reinforcing structures that actively manufacture the conditions that sustain them. Every clear day makes tomorrow's clear day more likely. And that leads directly into the forecasting problem, which is worth knowing about because it changes how you should read a heat forecast. Numerical weather models have a documented weakness with blocking patterns. They are generally good at seeing them form. They are considerably worse at predicting when they will break down, and the error runs consistently in one direction. Models tend to break these features down too early. Multiple episodes this summer outlasted the Windows forecast for them. That has a practical consequence that I think is underappreciated. If the peak intensity of a heat event is reasonably well forecast, but its duration is systematically underestimated, then the metric that matters most for human health is exactly the metric the guidance handles worst. Peak temperature determines the headline. Duration determines the death toll. Heat is a cumulative injury. The body does not reset each morning during a prolonged event. Sleep debt accumulates, dehydration accumulates, cardiovascular strain accumulates, and the risk on day 9 of a heat wave is meaningfully higher than the risk on day 2 at identical temperatures. So a forecast that gets the peak right and the duration wrong is a forecast that gets the danger wrong, even when every individual daily number verifies. It is worth being concrete about what the geometry of a ridge actually looks like, because the word suggests something narrow, and it is nothing of the sort. A ridge of this magnitude is a continental scale feature. Its axis may sit over the Great Basin, while its eastern flank extends across the Gulf Coast, and its influence reaches the Atlantic seaboard. That is precisely why a structure whose peak heights were measured over the desert southwest is capable of switching off thunderstorms in South Florida, 2,000 miles away. You're not looking at a local weather system. You're looking at a reorganization of the flow across most of a continent, and every location underneath it experiences a version of the same suppression, filtered through whatever local conditions it happens to have. The shape of the flow around the ridge matters too. When the jet stream develops large amplitude waves, it slows down. A fast, relatively straight jet moves weather systems along briskly and nothing sits anywhere for long. A highly amplified jet with deep troughs and tall ridges moves much more slowly, and in extreme cases the wave pattern becomes effectively stationary. Meteorologists have names for the specific configurations, the omega block and the Rex block among them, describing the shape the flow makes on a map. What all of them have in common is that they lock a pattern in place, and the location that ends up under the ridge stays under the ridge. The historical version of this is the one everybody has heard of without knowing the mechanism. The heat of the 1930s across the American plains, the summers that became shorthand for what extreme continental heat looks like, were produced by exactly this kind of persistent amplified pattern, amplified further by a land surface that had been stripped of moisture until it could no longer buffer anything. Once a surface dries out, its Bowen ratio climbs. More energy goes into heating instead of evaporating, and the ridge above it strengthens. Drought and heat feed each other through the same feedback we have been tracing all along. Notice what that means for a place like South Florida, which cannot dry out in the same way. The land surface feedback that amplified the plains heat is not available here. The moisture is not going anywhere because it is coming off an ocean. So a ridge over Florida cannot manufacture desert heat. What it can do is remove the two breaks that depend on circulation and leave the humidity break standing alone, holding the number down while the heat index climbs into a range the air temperature never reveals. Now connect all of that back to a single airport in South Florida. The ridge is the direct physical cause of two of Miami's 3 failed breaks. It generated the low-level flow pattern that stalled the sea breeze. It generated the subsidence that capped the convection. The record ridge and the record adjacent temperature are not two separate stories that happen to be occurring at the same time. They are one event, measured in two different places, and this thing is not sitting over one city, it is sitting over most of a continent. Part 7. 80 million people, under one piece of sky. 30 million Americans under extreme heat risk, 50 million more under major heat risk, 80 million people, which is close to a quarter of the population of the United States, all of them living underneath a single atmospheric feature at the same time. That is the scale of what we are describing, and it is worth pausing on because we have a habit of discussing weather one city at a time, and it disguises how large these things actually are. Extreme heat warnings, heat advisories and related alerts have been active across the central, southern and eastern United States through this stretch. Heat index values have run between 105 and 115 degrees, from the Gulf Coast through the southern plains and out into the desert southwest. Values above 105 and locally past 110 have been recorded in southern Georgia, coastal South Carolina, the Florida Panhandle, and the mid-south region around Memphis. At least 9 daily maximum temperature records were expected to fall over the preceding weekend alone, with several more challenged and dozens of high and low records likely to break through the week. The Weather Prediction Center had record-breaking warmth expanding westward into the desert southwest by Wednesday, with high temperatures in the low 110s. Underneath those numbers is an operational framework most people have never heard of, and it is worth knowing about because it is quietly changing how this country handles heat. The National Weather Service runs a product called Heat Risk. It is a 4-tier scale running from level 1, minor, through level 4, extreme, and unlike a simple temperature threshold, it incorporates how unusual the heat is for that specific location and time of year, how long it will last, whether the overnight period offers relief, and whether the values are at levels associated with health impacts. That last point is the important one. Heat Risk was not built by asking what temperature sounds dangerous. It was built by looking at where health effects actually appear in the data. Level 3 and Level 4 days correlate with measurable surges in emergency department utilization. It is not an abstraction. It is a scheduling signal for hospitals. The framework also encodes something the old thresholds missed. 95 degrees in Miami in August is unremarkable. 95 degrees in Portland, Maine in June is a public health emergency because the housing stock has no air conditioning and the population has no acclimatization. Absolute temperature was never the right measure. Departure from local normal, combined with duration, is much closer. And duration brings us to the part of this event that is genuinely historic, and it is not happening during the day at all. Record warm overnight lows in the low 80s have been recorded along the Gulf Coast during this episode. Forecasters have pointed at those numbers rather than the afternoon highs when explaining why this heat is dangerous rather than merely miserable. The national context makes the point better than any single station can. July of 2026 set the record for the warmest average overnight minimum temperature ever recorded across the contiguous United States. The value was 64.2 degrees Fahrenheit, which is 3.7 degrees above average, and it beat the previous record set in July of 2022 by 7/10 of a degree. I want to explain why 7/10 of a degree is a large number, because it sounds small. When you average a measurement across an entire continent, you're averaging across thousands of stations in wildly different conditions. Some places are hot, some are cool, some are wet, some are dry, and the extremes cancel each other out. That cancellation is what makes national averages stable. Records at that scale usually fall by hundredths or a tenth or two, because it takes a broad, coherent, continent-wide anomaly to move the whole distribution at once. Beating a national average by 7/10 of a degree means it was not a few hot stations dragging the number up. It means the entire country was warm at night together. More than 90 United States temperature records were forecast to fall during a single week in mid-July, and the majority of them were overnight low records rather than daytime high records. Places with no reputation for heat at all were forecast to hold above 70 degrees through the night. Fargo, North Dakota, International Falls, Minnesota, Portland, Maine, cities whose identities are built around winter. There is a physical reason the nights are moving faster than the days, and it is clean. Daytime maximum temperatures are constrained by a long list of competing processes. Cloud cover interrupts them, convection interrupts them, evaporation from soil and vegetation buffers them, wind mixes them. There is a great deal of machinery that limits how high the afternoon can go, and much of it responds to the warming itself. Nighttime minimum temperatures are constrained by essentially one process: radiative cooling. The surface sheds heat to space as infrared radiation, and the rate at which it can do so depends almost entirely on what is in the air column above it. Water vapor absorbs and re-emits that radiation. More vapor in the air means a slower loss, which means a warmer floor. So the overnight minimum is a much more direct readout of what is happening to the atmosphere's composition and moisture content than the daytime maximum is. It has less noise in it, it is the cleaner instrument, and it happens to be the number most closely tied to mortality, because heat kills through cumulative load, and the load only decreases when the body gets a period cool enough to recover in. It is also worth understanding why the alerts vary so much from place to place, because it looks arbitrary from the outside, and it is not. A heat advisory in Maine and a heat advisory in Texas are issued at completely different temperatures, and the reason is that the National Weather Service is not trying to describe the weather. It is trying to describe the risk, and risk depends on what a population is prepared for. Acclimatization is real, and it is measurable. A body exposed to heat repeatedly over 1 to 2 weeks adapts. Plasma volume increases, sweating begins at a lower core temperature, sweat becomes more dilute so less salt is lost, and cardiovascular strain at a given heat load drops substantially. Someone who has spent the summer in Houston is a physiologically different machine from someone who has spent the summer in Minneapolis, and the same 95-degree afternoon is a routine day for one and a genuine emergency for the other. Infrastructure matters just as much. Air conditioning penetration varies enormously by region, and where it is uncommon, the housing stock is often built to retain heat rather than shed it. A well-insulated northern building that holds warmth through a February night holds it through an August night just as effectively, and a top-floor apartment in a heat wave can run substantially warmer than the outdoor air for days after the outdoor peak has passed. That is the reason a single national temperature threshold would be useless, and it is the reason the framework moved toward measuring departure from local normal, duration, and overnight relief instead. It is also the reason the Miami-Dade pilot exists at all, which we will come to shortly, which is where this connects back to Miami. Every one of the city's 3 breaks is a daytime mechanism. Humidity suppresses the daytime maximum. The sea breeze fires during the afternoon heating cycle. The storms build when the sun is highest. None of them do anything at 3 in the morning. A coastal subtropical city has excellent protection against the peak. It has none whatsoever against the night. Part 8. The desert. At the other end of the ridge. To see what Miami's protection is actually worth, look at what the same ridge does to a place that has none. Phoenix has been forecast to run between 110 and 111 degrees through Friday, with an extreme heat warning in effect for the city and southwestern Arizona. It has recorded 28 days at or above 110 degrees so far in 2026. The first 3 days of August all exceeded 110. Regional temperatures have been running 10 to 15 degrees above normal for mid-August. Same ridge, same subsidence, same clear sky, no ocean anywhere near it, no humidity buffer, nothing to convert the solar budget into vapor, and so the full energy load goes straight into temperature. The desert does not lose any breaks during a heat event, because it never had any to lose. The human cost of that is being counted right now, and the way it is being counted tells you something important. Maricopa County health officials have confirmed 63 heat-related deaths so far in 2026. They have another 558 deaths still under investigation, 63 confirmed, 558 pending, roughly 1 to 9. That ratio is not a sign of uncertainty about whether heat is dangerous. It is a sign of how slow and conservative the confirmation process is. Determining that heat caused a death requires medical examiner review, toxicology in many cases, environmental exposure history, and a judgment about contributing conditions. It takes months. Meanwhile, the deaths keep accumulating and the confirmed count lags far behind, which means every heat death number you hear reported during an active heat wave is a flaw. Not an estimate, a flaw. The real figure for this summer will not be known until long after the summer is over, and it will be substantially larger than 63. We covered the front end of this pattern in our video from July 25th on the heat dome sitting over the southwest, and one number from that day has stayed with me. Sky Harbor hit 117 degrees at 14 minutes past 3 in the afternoon on July 24th, which set a new daily record. But the number that mattered was the one that came after dark. The overnight low that night was 97 degrees, which tied the warmest low ever recorded there. 97 degrees at the coolest moment of the night. That is a city that never dropped below the threshold where the human body can recover, for an entire 24-hour cycle. Nationally, this is why heat sits where it sits in the mortality statistics. Heat kills more Americans in an average year than hurricanes, tornadoes, and floods combined. The Systematic Centers for Disease Control Tracking recorded 2,415 heat deaths in 2023, which is the highest figure in the record, and 2,394 in 2024, the second highest. Cumulatively, since 2020, the United States has recorded more than 9,436 heat-related deaths, and those are flaws too, for a reason we will develop in detail later. Heat rarely appears on a death certificate as the underlying cause. What appears is the cardiac event or the renal failure that the heat triggered. There is one more asymmetry between the two places worth stating, and it runs opposite to what you might expect. The desert has no breaks during the day, but it has an extraordinary one at night. Dry air is transparent to infrared radiation, so once the sun goes down, the ground sheds heat to space at a rate that a humid climate cannot approach. That is why the Sonoran Desert has historically dropped 30 or 40 degrees overnight, and it is why the region has been survivable at all without mechanical cooling for as long as people have lived there, which makes the July 24th number genuinely disturbing rather than merely impressive. 97 degrees at the overnight low means that in the one place on the continent with the strongest natural nighttime cooling mechanism, that mechanism produced almost nothing. Some combination of urban heat storage in the enormous thermal mass of a paved metropolitan area and elevated atmospheric moisture held the floor up all night. The desert's one advantage was neutralized, so both places are losing protection. Phoenix is losing the night. Miami is losing the day. They are the same story told through opposite mechanisms, and the connective tissue between them is a single ridge and the ocean state underneath it. So the desert gives us the contrast that makes Miami legible. Phoenix's story is a story about magnitude, about how high a number can go when nothing stands in its way. Miami's story is a story about the removal of protection, about a city that has always had something standing in the way, and suddenly does not. That is why a 99-degree afternoon on the Florida coast belongs in the same conversation as a 111-degree afternoon in Arizona, even though one of those numbers is 12 degrees larger. But the ridge only explains part of it. The ridge explains the capped storms and the stalled breeze. It does not explain why the water underneath Miami is behaving the way it is, and it does not explain why the brakes were vulnerable in the first place. For that, we have to stop looking up. Part 9. The Summer of 46 Days. 46. That is not a temperature. It is a count of consecutive days, and it belongs to the summer of 2023, and it is the single most important number in Miami's climate record that almost nobody outside South Florida has ever heard. For 46 days in a row, the afternoon heat index in Miami climbed above 100 degrees every single day. The streak began on June 11th and ended on July 27th, and it did not end because the pattern relaxed or the season turned. It ended because heavy rain fell and capped the heat index at 98. The previous record for consecutive days above that threshold was 32, set in 2020. So the record did not creep. It jumped from 32 to 46, an increase of 44%, in a statistic that had presumably crawled upward by a day or two at a time across the preceding century. That is worth sitting with, because in climate records, jumps of that size are unusual, and they carry information. When a record inches upward, you are watching the tail of a distribution get sampled a little more thoroughly. When a record leaps by nearly half its previous value, you are usually watching the distribution itself move. The rest of that summer's ledger reads like an institution running out of vocabulary. Miami set 10 daily temperature records. It set 27 daily heat index records. It received the first excessive heat warnings ever issued for the city by the National Weather Service, in a place that had been operating without that particular product for its entire modern history. It spent 23 days under heat advisories, and through every single day of it, the air temperature never reached 100 degrees. Read that again, because it is the hinge of this entire video. The worst heat event in the modern history of Miami, an event so far outside the historical envelope that the Weather Service had to invent new warnings for it, did not come close to touching the 1942 record. The record survived the summer that broke everything else. That fact is either evidence that nothing has changed, or it is evidence that we have been measuring the wrong thing. It cannot be both. And by the end of the next section, you are going to know which one it is. There was an institutional response to that summer that I think is the most revealing detail in the whole story, and it got almost no national coverage. In May of 2023, the National Weather Service began an experimental pilot program specifically for Miami-Dade County. The pilot lowered the heat index thresholds at which heat advisories and heat warnings are issued. Miami-Dade is the only area in the country where the Weather Service has run this pilot. Think about what that means as an admission. The agency responsible for warning Americans about dangerous weather looked at its own criteria for South Florida and concluded that those criteria were not describing the risk in that specific place. The thresholds were letting dangerous days pass without a warning, so they lowered them for one county as an experiment. Agencies do not do that casually. Changing a warning threshold changes false alarm rates, changes public trust, changes the legal and operational picture for every county emergency manager downstream. You do it when the evidence is strong enough that leaving the old threshold in place is the greater risk. And notice what the change was about. Not temperature, heat index. The pilot exists because the number that describes danger in South Florida is not the number the record books archive. There is a physiological reason a streak record is worse news than a magnitude record, and it comes down to how heat injures a body over time. A single hot afternoon is survivable for almost anyone with water and shade, because the night restores what the day took. The body rehydrates, core temperature returns to baseline, cardiovascular strain relaxes, and sleep does the repair work it is supposed to do. Take away enough consecutive nights and none of that happens. Fluid deficits carry over, electrolyte balance drifts, sleep quality degrades, which impairs judgment about hydration and exertion, which deepens the deficit the following day. Cardiovascular strain accumulates in people whose reserve is already limited. Epidemiological studies of heat waves consistently find that mortality does not scale with peak temperature nearly as strongly as it scales with duration, and that the deaths cluster in the back half of an event rather than on its hottest day. Which means the 46-day streak was, in human terms, a far more serious event than any single afternoon Miami has ever recorded, including 1942. And it produced no all-time record of any kind. The record book has no column for it. That is the second time in this story we have run into the same problem from a different direction. The metrics that describe danger and the metrics that define history are not the same metrics, and the gap between them is where the risk hides. Now put 2023 next to today because they are two completely different failure modes, and the contrast is instructive. 2023 was a grind. 46 days of relentless, cumulative, unglamorous heat, none of which produced a single spectacular number. It was dangerous the way a long illness is dangerous, through accumulation rather than through any individual moment. And in terms of the record book, it produced almost nothing worth headlines, because the metric the headlines used never moved. Today is the opposite. One afternoon, a single value, sitting 1 degree from a number that has stood for 84 years. It is a spike rather than a plateau, and it is legible in a way the 46 days never were. But both events are outputs of the same underlying change, and the reason they look so different is that they hit the system in different places. The long grind of 2023 was a moisture story. Dew points elevated, heat index elevated, nights warm, no relief, day after day, with the humidity break holding the air temperature down the entire time. Today is a circulation story. The moisture is still there, but the breeze has stalled and the storms are capped, so the air temperature is free to climb in a way it was not free to climb during those 46 days. Two different mechanisms, one underlying cause, and the underlying cause was visible in 2023 if you were looking at the water instead of the air. That is the summer when a sensor in Manatee Bay, near Everglades National Park, read 101.1 degrees Fahrenheit at 6 in the evening. That is the summer when a coral restoration site off South Florida recorded 100% mortality, every colony dead. NOAA's guidance is that coral reefs generally thrive in water between 73 and 84 degrees. Total mortality at a restoration site is not a subtle signal, and it is not a signal that has any dependence on how a weather station was sited or what the pavement around it was made of. Coral does not care about parking lots, so the water was already telling the story in 2023. Nobody framed it that way, because the number everyone watches, the number that defines what counts as a record, never moved. It is about to become clear why. Part 10. The number nobody records. Let me ask a question about instruments rather than about weather, because I think it is the question this entire event is really posing. What if the measurement we have built our entire concept of a heat record around is the wrong measurement for half the country? The air temperature is a beautiful quantity for a climate record. It is easy to measure, it has been measured the same way for well over a century, the instruments are cheap and reliable, and the resulting archive is long and continuous. Almost everything we know about the changing climate rests on it. There is nothing wrong with the number, but the air temperature describes the air. It does not describe what the air does to a person, and in a dry climate those two things are close enough that the difference does not matter much. In a saturated marine climate they diverge enormously, and the divergence is not a small correction. It is the entire story. That is what the heat index exists to capture, and it is worth being precise about what it actually is, because feels like is a phrase that makes it sound subjective, and it is not. The human body maintains a core temperature within about 1 degree of 37 degrees Celsius, and it is a heat engine that is constantly producing waste heat that has to go somewhere. At rest, a person generates roughly the heat output of a small light bulb continuously. Under exertion, it can be 5 or 10 times that. When the air is cooler than skin, some of that heat leaves by conduction and convection. Once the air is warmer than skin, those channels reverse, and the body begins gaining heat from its environment rather than losing it. At that point there is exactly one mechanism left: evaporation. Sweat on the skin absorbs energy from the body as it changes phase from liquid to vapor, exactly the same physics that keeps the air temperature down over the Everglades. It is a remarkably powerful cooling system, capable of shedding enormous heat loads, and it has one dependency. The rate of evaporation is governed by the difference in water vapor pressure between the wet skin and the surrounding air. When the air is dry, that gradient is steep, evaporation is fast and the system works. When the air is already loaded with vapor, the gradient collapses. Sweat still leaves the body. It just does not evaporate. It runs off, taking water and electrolytes with it, and removing almost no heat at all. The cooling system is running at full power and delivering nothing. That is the physiological content of a dew point reading, and it is why the heat index is not a comfort scale. It is an estimate of how hot the air would have to be, at a reference humidity, to impose the same physiological load. It is an attempt to translate the environment into the units the body actually experiences, which brings us back to today's two numbers: 99 degrees of air, 110 degrees of heat index, 11 degrees of separation, and every one of those 11 degrees is made of water vapour. Now, the comparison that I think reframes the entire national conversation about heat. A 99-degree afternoon in Miami with a 110-degree heat index imposes a greater physiological load than a 110-degree afternoon in Phoenix at low humidity. In the desert, at 110 degrees with a dew point in the 40s, the evaporative channel is wide open. The body is under strain, it needs water, it needs shade, but its primary cooling mechanism is functioning at close to full efficiency. In Miami at 99 with a dew point in the upper 70s, that mechanism is throttled. The desert number is bigger, the coastal number is worse, and only one of those two numbers goes into the record book as a candidate for an all-time high. That is the structural bias I want you to see clearly. The archive tracks air temperature. Air temperature is the quantity that humidity suppresses. Therefore, the archive systematically undercounts change in exactly those places where humidity is rising, which are the places where rising humidity is most dangerous. It is not a conspiracy, and it is not an error. It is a measurement designed for a general purpose being applied to a place where it answers a different question than the one we need answered. 2023 is the proof, sitting right there in the ledger: 10 daily temperature records, 27 daily heat index records, nearly 3 to 1. The metric that moved is the metric nobody treats as a record, and the metric that barely moved is the one that defines what counts as history. There is a related measurement that takes this further, and it is worth understanding because it sets the outer boundary of the entire problem. The wet bulb temperature is what a thermometer reads when its bulb is wrapped in a wet cloth with air moving over it. It is, functionally, the temperature of a perfectly sweating surface, and therefore it is the lowest temperature any object can reach through evaporation alone in that air. For roughly 2 decades, the number cited as the limit of human survivability has been a wet bulb temperature of 35 degrees Celsius. That is 35 degrees at complete saturation, or roughly 46 degrees at half humidity. The logic is elegant. If the wet bulb temperature exceeds skin temperature, then no amount of sweating can cool you, and core temperature rises regardless of how healthy or hydrated or shaded you are. It becomes a physics problem rather than a fitness problem. That number appeared in countless papers, articles, and policy documents, and it had never actually been tested on people. When researchers at Penn State finally tested it, in the project known as PSU Heat, they put 11 men and 13 women between 18 and 34 years old in a controlled chamber, had them pedal a cycle ergometer at low intensity to simulate ordinary daily activity, and stepped them through 6 carefully controlled combinations of temperature and humidity while watching core temperature. They were looking for the critical environmental limit, the point at which the body can no longer hold its core temperature steady and begins an uncontrolled rise. They found it at roughly 30.6 degrees Celsius wet bulb, not 35, 30.6. In young, healthy, hydrated adults doing almost nothing, under laboratory conditions with none of the complications of real life. We covered this in the wet bulb video back in June, and the implication has not gotten less serious since. The margin everyone assumed existed is about 4.5 degrees smaller than the number that has been in the literature for 20 years, and for older adults, for people with cardiovascular or renal conditions, for anyone working outdoors, the real limit sits lower still. So the picture assembles like this. The property that has protected Miami's air temperature record for 84 years is water vapour. The property that disables human thermoregulation is water vapour. The city's protection and the city's danger are the same molecule, and the record book only counts one of them. Which raises the obvious question: where is all that water vapour coming from? Part 11. The ocean changed state. I have been letting you carry an assumption through this entire video, and it is time to take it away. I told you there were 3 breaks: humidity, the sea breeze, the afternoon storms. I described them as 3 separate systems, and that framing is useful for understanding the mechanisms, and it is wrong in the way that matters most. They are not 3 systems. They are 3 outputs of one system, and that system is the ocean. Trace them back. The humidity is water evaporated from the sea surface, delivered inland by the marine air mass. The sea breeze is driven by the temperature difference between the land and that same sea surface. The storms are built when two sea breezes, both of them products of the same ocean, collide and force air upward through a column made humid by the same evaporation. Every break draws on one input, which means you do not need three separate failures to remove all three breaks. You need one change in the water. That is the structural insight of this whole event, and it generalizes far beyond Miami. A system with three redundant safeguards that all depend on a single upstream input has no redundancy at all. It has one point of failure wearing three costumes. Engineers call this common cause failure, and it is the reason a backup generator on the same flooded floor as the primary is not a backup. South Florida's climate has been running on exactly that architecture for as long as the city has existed, and nobody had reason to notice because the input had never changed. It has changed. Sea surface temperatures in the Gulf of Mexico have been running at record daily highs, roughly 1.8 degrees Celsius above the 1982 to 2011 baseline, at points earlier in 2026. In Fahrenheit terms, that is a bit over 3 degrees, averaged across an entire ocean basin, in a fluid with an enormous heat capacity that resists changing temperature, moving a basin that far takes an extraordinary amount of stored energy. The seasonal average for Gulf water in August runs between 84 and 88 degrees Fahrenheit, with local values reaching 92. Hold that number in your head and walk it through each break in turn because the consequences are not intuitive and they are not all in the same direction. Break 1. The humidity. Under a warmer ocean. Evaporation accelerates. The relationship between temperature and the amount of water vapor air can hold is not linear, it is exponential. So a warmer sea surface loads the air far more heavily than a proportional increase would suggest. Dew points climb, so the humidity break actually gets stronger. It suppresses the air temperature more effectively than it used to, and that is precisely why it is dangerous. The protection intensifies, and the heat index climbs, and the record book records neither. The break converts directly into risk. Break 2. The sea breeze under a warmer ocean. Here the effect runs the other way. The circulation is powered by the temperature contrast between land and water, and warming the water shrinks the contrast. The pressure gradient weakens, the circulation forms later, moves slower, penetrates less far inland, and arrives carrying air that is closer to the land temperature than it used to be. At some point along that spectrum, the sea breeze stops being a cooling mechanism at all. It is still a wind. It is just no longer bringing anything cool. Break 3. The storms under a warmer ocean. This one is the most counterintuitive. A warmer ocean means more moisture, and more moisture means more energy available for convection, so you would expect more storms, not fewer. And in the absence of a ridge, that is exactly what you get. But convection needs two things, not one. It needs moisture, and it needs lift. The moisture is abundant. The lift comes primarily from sea breeze convergence, and we just weaken the sea breezes. Add a strong ridge capping what remains, and you have an atmosphere that is loaded with energy and has no way to release it. The fuel is there. The ignition is gone. That is why today's setup is so strange to look at. It is not that the atmosphere lacks the ingredients for a storm. It has more of them than usual. It simply cannot get started, and every hour it fails to get started, the surface keeps absorbing sunlight it would otherwise have been shielded from. It is worth pausing on the scale of energy involved, because ocean temperature anomalies get quoted in the same units as air temperature anomalies, and that comparison badly understates them. Water has a specific heat capacity roughly 4 times that of air by mass, and seawater is about 800 times denser. Raising the temperature of a cubic meter of ocean by 1 degree takes something on the order of 3,000 times the energy required to raise a cubic meter of air by the same amount. When you read that a basin the size of the Gulf of Mexico is running 1.8 degrees Celsius above its baseline, you're not reading about a warm spell. You're reading about a quantity of stored energy that has no meaningful comparison in ordinary human experience. And unlike the atmosphere, the ocean does not shed it overnight. Air temperature anomalies can appear and vanish in a day. A basin-scale ocean anomaly persists for months, because the thermal inertia that makes the ocean slow to warm makes it equally slow to cool. That persistence is exactly why the ocean, not the atmosphere, is the thing to watch. The air tells you about today. The water tells you about the next season. It also explains why the 3 breaks cannot recover quickly, even if the ridge collapses tomorrow. Break the ridge, and the sea breeze returns and the storms rebuild, and the surface temperature drops the same afternoon. But the water underneath will still be 1.8 degrees above baseline, still loading the air with vapour, still shrinking the land-sea contrast, still holding the overnight minimum up. The circulation breaks come back. The condition that weakened them does not. Now look at what the water has been doing outside the Gulf, because there is a witness in this story with no station sighting problem and no urban heat island. Coral. NOAA's guidance is that reefs generally thrive between 73 and 84 degrees Fahrenheit. Corals live in symbiosis with algae that provide most of their nutrition, and when water temperature rises past a narrow tolerance, the coral expels the algae. That is bleaching. A bleached coral is not dead, but it is starving, and if the heat persists, it dies. In 2023, a coral restoration site off South Florida recorded 100% mortality. Not a percentage of the colonies, all of them. And that same summer, the sensor in Manatee Bay read 101.1 degrees. The record status of that reading remains contested, legitimately, because a shallow, murky enclosed bay is not the open ocean, and the site is not comparable to a mid-ocean buoy. But the sensor worked. The water was that temperature. Coral has been building reef structures in Florida waters for thousands of years. It is, in effect, the longest-running thermometer in the region, and it is telling you how far outside the historical envelope the water has moved, without reference to any human measurement at all. So the record from 1942 was never really a record about air. It was a record about water. It measured how much protection the ocean around Miami was willing to provide on the worst possible afternoon, and it stood for 84 years, because that answer stayed the same for 84 years. The answer has changed, and something reorganized that ocean to change it, something that is not finished and is not local. Part 12. 2.6 degrees. In the wrong ocean. Plus 2.6 degrees Celsius. That was the weekly Nino 3.4 index as of August 10th, 2026, and it is the number that sits underneath everything we have discussed. Let me explain what that index actually is, because it gets referenced constantly and defined almost never. Nino 3.4 is a specific rectangle of the Pacific Ocean, straddling the equator in the central and eastern basin. Scientists measure the sea surface temperature inside that box and compare it to the long-term average for that time of year. The difference is the anomaly. It is the standard operational measure of where the El Niño Southern Oscillation sits at any given moment. Plus 2.6 degrees Celsius is a very large anomaly. For context, an event is generally classified as strong when the smoothed index exceeds 1.5 degrees. The smoothed version matters more than the weekly value, because weekly numbers bounce around and the atmosphere responds to sustained conditions rather than momentary ones. The official 3-month Oceanic Niño Index for May through July of 2026 came in at plus 1.39 degrees Celsius. That is a genuine, established, moderate to strong El Niño already in place. NOAA's Climate Prediction Center has an El Niño advisory in effect. Forecasters put the odds of the event persisting and strengthening through the 2026 to 27 Northern Hemisphere winter at 97 to 99%. NOAA gives 90% odds that it reaches strong or very strong status during August, September and October. 97 to 99% is not a normal forecast confidence. In seasonal climate prediction, that is about as close to certainty as the field ever gets, and it reflects the fact that once an El Niño is established in August, the ocean's thermal inertia makes its persistence through winter nearly mechanical. Now the sentence that carries this entire act: the event has not peaked. Everything we have looked at in this video, the record adjacent temperature in Miami, the record intensity ridge, 80 million people under heat alerts, the warmest average overnight minimum ever recorded across the contiguous United States, the Gulf running 1.8 degrees above baseline, all of it is happening on the leading edge of a forcing that is still strengthening. The peak, by NOAA's own guidance, is months away. So what is an El Niño physically? It is worth walking through properly, because it is usually described in a way that makes it sound like a warming event, and it is really a redistribution event. Under normal conditions, trade winds blow from east to west across the tropical Pacific. They drag surface water westward, piling warm water up in the western Pacific near Indonesia. Sea level there is measurably higher than off South America, and the warm layer is deeper. In the east, that westward drag pulls surface water away from the South American coast, and cold water wells up from below to replace it. That is the normal state, and the temperature contrast across the basin is what keeps the trade winds blowing in the first place. An El Nino begins when the trades weaken. The warm water piled in the west sloshes back east. Upwelling in the east slows or stops. The eastern Pacific warms, the temperature contrast across the basin shrinks, and the trades weaken further. Another self-reinforcing loop, exactly the same shape as the ridge feedback. The atmospheric consequences follow from where the warmest water sits, because that is where the deepest convection happens. Move the warm pool east, and you move the towering thunderstorm complexes east with it. And those complexes are the primary heat engine of the tropical atmosphere. Moving them redistributes where heat is being pumped into the upper atmosphere, which changes the pressure patterns downstream, which shifts the position and strength of jet streams across the hemisphere. This is the mechanism by which a change in ocean temperature near the equator rearranges weather thousands of miles away. The technical term is teleconnection, and it is why the state of a rectangle of ocean off Peru is relevant to whether it rains in Miami. Now, the honest caveat, and I want to give it properly rather than gloss it, El Niño's classic and best documented North American signature is a winter signature, wetter across the southern tier, milder across the north, a southward displaced jet. The summer teleconnections are weaker, more variable, and much harder to attribute confidently. A summer featuring a strengthening El Niño, record Gulf warmth, a record intensity ridge, and a nearly empty Atlantic basin is a combination with limited historical precedent at this intensity, and untangling how much of today's heat is El Niño driven, how much is El Niño amplified, and how much is simply concurrent with its development is genuine research that will take years to settle. So I'm not going to tell you the El Niño cause this afternoon in Miami. What I will tell you is that the ocean state underneath the entire event is anomalous in a way that is measured, documented, and still strengthening. And that leads to the point that resolves the false choice people keep being offered. You will hear that El Niño explains all of this, and therefore the longer-term warming is irrelevant. That argument fails on a simple physical fact. El Niño does not create heat. It moves heat that is already in the ocean from one place to another and changes where it interacts with the atmosphere. It is a redistribution mechanism operating on top of a baseline. The baseline is what has changed. A moderate El Niño occurring on a warmer ocean produces different absolute numbers than the same El Niño occurring on a cooler one, and the sea surface temperatures we are seeing in the Gulf are the arithmetic result of both terms. There is a second, quieter consequence of that ocean state that deserves a mention here, because it feeds directly back into everything we have discussed about Miami. El Niño's atmospheric response includes changes to the position and strength of the subtropical ridge over North America, and a displaced or strengthened ridge is precisely the structure that caps convection and stalls sea breezes. So the chain runs from a rectangle of warm water on the equator, through the displacement of tropical convection, through the adjustment of the hemispheric flow, to a capping inversion over South Florida on a Tuesday afternoon in August. That is a long chain with real uncertainty at several links, and I am not going to pretend each link is nailed down, but it is a physically coherent chain. Every step of it is a documented process, and it terminates exactly where our story is. We looked at the early read on this reorganization in our video from July 24th on what the two ocean basins were doing, when the Atlantic could not manage to start a single storm while the Pacific built them one after another. That contrast was the fingerprint of the same shift. At the time it looked like a story about hurricanes. It was a story about this, which leaves the question that closes this act, and it is the one I cannot answer for you. If a forcing that has not yet reached its peak has already pushed the hardest to heat major city in the continental United States to within 1 degree of a record it has touched exactly once in 130 years, what does the peak look like? Part 13. The Hurricanes That Never Formed. There is an absence in this story that nobody is reading as a warning, and it should be. Through early August of 2026, the Atlantic hurricane season has produced 2 named storms, Arthur and Bertha. It has produced 0 hurricanes, not 0 major hurricanes, 0 hurricanes of any category. NOAA raised its probability of a below-normal season from 55% to 75%. The revised outlook calls for 7 to 13 named storms across the whole season, 2 to 6 hurricanes, and 0 to 2 major hurricanes, down from 8 to 14 named storms in the May forecast. At the point this pattern set in, the basin was free of active tropical systems entirely, with the National Hurricane Center forecasting no formation over the following 7 days. That is happening during the climatological ramp toward the peak of the season. Mid-August is when the Atlantic normally starts producing storms in earnest, as African easterly waves move off the continent into water that has spent all summer absorbing sunlight. The fuel is there, the Atlantic is warm, the storms are not forming, the mechanism is the same El Nino we just spent a section on, acting through a completely different pathway. When tropical convection shifts east into the central Pacific, it alters the upper-level flow across the entire tropical belt, strengthening westerly winds high above the Atlantic and Caribbean. Meanwhile, the low-level trade winds continue blowing from the east. The result is vertical wind shear, a change in wind direction and speed with height across the depth of the atmosphere. A tropical cyclone is a vertically stacked structure. It requires its circulation to remain aligned from the surface to the upper troposphere so that the heat released by condensation stays concentrated in the core and reinforces the low-pressure center underneath it. Shear tilts that stack. The upper circulation gets displaced downwind from the lower one. The released heat gets ventilated away instead of accumulating. Dry air gets entrained into the core, and the storm is decapitated before it can organize. There is a detail in the seasonal forecast worth pulling out, because it shows how confident the agencies became. NOAA did not merely maintain a below-normal outlook. It raised the probability from 55% to 75% as the season progressed, which is the opposite of what usually happens. Seasonal forecasts normally converge toward climatology as the peak approaches, because the window for surprises narrows in both directions. Raising a below-normal probability in August means the ocean signal became clearer, not murkier, at exactly the point when the atmosphere should have been hardest to predict. The revision to the storm count tells the same story. The May outlook allowed for 8 to 14 named storms. The August update pulled the top of that range down to 13 and the bottom to 7, and cut the major hurricane range to 0 to 2. A forecast that allows for the genuine possibility of a season with no major hurricanes at all issued in the middle of August is a forecast that has stopped hedging. So the same ocean state that loaded the atmosphere with moisture and helped park a record ridge over the continent is simultaneously preventing the Atlantic from producing anything at all. And here is why that matters for a video about heat. A tropical system is the one weather event powerful enough to override all 3 of Miami's failed breaks at once. It brings deep cloud cover that shuts off insulation for days. It brings rain measured in inches per hour. It brings a wind field that completely overwhelms any local pressure pattern, including a ridge. Even a disorganized tropical wave passing well offshore drags enough moisture and cloud across South Florida to break a heat pattern for 2 or 3 days. Historically, that is one of the main things that ends a Florida heat wave in August. The tropics interrupt it. This year, the ocean has arranged for there to be nothing to interrupt it with. Consider how much water a single tropical system moves. A mature tropical cyclone releases latent heat at a rate that has been compared to the detonation of a large nuclear device every few minutes, and it does that continuously for days. All of that energy comes from evaporating ocean water and condensing it as rain, which is why the storm cools the sea surface behind it, leaving a visible cold wake that satellites can track for a week afterward. That cold wake is the point. A hurricane does not just interrupt a heat wave with clouds and rain. It physically removes heat from the upper ocean, mixing cooler water up from below and carrying warmth into the atmosphere and out of the region. The Atlantic storms are one of the mechanisms by which the basin sheds accumulated summer heat. So a season with no hurricanes is not a neutral outcome for the water. It is a season in which one of the ocean's own cooling processes does not run. That is the part that gets lost when the seasonal forecast is reported. A quiet hurricane season reads as good news. It is reported as good news. And for coastal property and for anyone who has lived through a landfall, it genuinely is. But the quiet Atlantic and the record heat are not 2 separate stories, one good and one bad. They are 2 outputs of the same ocean state, and the same forecast that removes the storms also removes the thing that breaks the heat. You're not getting a mild summer instead of a bad hurricane season. You're getting a heat season with the off switch disabled. Part 14. What humid heat does to a human body. Consider the body as a machine with a very narrow operating tolerance. Core temperature has to stay within roughly a degree of 37 degrees Celsius. Below that range, enzymatic processes slow. Above it, proteins begin to lose their shape, cell membranes destabilize, and the cascade that follows is fast and difficult to reverse. Everything the body does about heat is engineering in service of that one constraint, and the engineering is more elaborate than most people realize. The first response is circulatory. Blood vessels near the skin dilate, and blood flow to the surface increases dramatically, carrying heat from the core outward to where it can be shed. That sounds simple, but it has a cost. Blood that has moved to the skin is blood that is not in the central circulation, so the heart has to increase its output to keep pressure and perfusion adequate everywhere else. In a serious heat load, cardiac output can rise substantially, and it stays elevated for as long as the load persists. The second response is sweating, and we have already established what happens to it when the air is saturated. What I want to add here is what that failure costs, because it is not neutral. Sweat that does not evaporate still leaves the body. Water and electrolytes go out through the skin and do essentially no thermal work. So in high humidity, the body pays the full price of sweating, dehydration and electrolyte loss, and receives almost none of the benefit. Dehydration then reduces blood volume, which forces the heart to work harder still to maintain the elevated output that skin perfusion requires, which raises the metabolic heat production of the heart itself. That is the trap. In humid heat, the two cooling systems interfere with each other. Vasodilation demands more circulating volume. Ineffective sweating removes circulating volume. The system fights itself, and the strain lands squarely on the cardiovascular system. This is why heat kills the way it does. The dramatic picture of heat stroke, core temperature above 40 degrees Celsius with neurological collapse is real, and it does happen, but it is the minority of heat deaths. The majority are cardiac and renal. The heart fails under sustained elevated demand in someone whose reserve was already limited. The kidneys fail from the combination of dehydration and reduced perfusion. Someone with heart disease or diabetes or on medications that impair sweating or fluid balance dies during a heat wave of something that does not have the word heat anywhere near it on the paperwork, which is the mechanism behind the undercount, and it is worth being precise about because it is frequently described as a controversy when it is really a documentation artifact. Death certificates record an underlying cause. If a 78-year-old with existing cardiac disease dies during a heat wave in an apartment with no working air conditioning, the underlying cause recorded is very often the cardiac event. Heat may appear as a contributing factor if the certifier considered it, and it may not appear at all. There is no conspiracy required for this to systematically undercount. It is simply how the classification system was designed, and it was not designed with environmental exposure in mind. The Maricopa County numbers show the same process visible in real time. 63 deaths confirmed as heat-related so far this year, against 558 still under investigation. Those 558 are not a guess. They are cases where a medical examiner has flagged heat as a possible factor, and the determination has not been completed. Some fraction will be confirmed, some will not, and the process takes months. The national figures with all of that built into them are still enormous. The systematic tracking recorded 2,415 heat-related deaths in 2023, the highest in the record, and 2,394 in 2024, the second highest. Cumulatively, since 2020, more than 9,436. Heat kills more Americans in an average year than hurricanes, tornadoes, and floods combined. And it does it without producing a single photograph that looks like a disaster. There is a demographic pattern in heat mortality that follows directly from the physiology, and it is remarkably consistent across events and across countries. The deaths concentrate among the elderly, and specifically among the elderly living alone. Several factors stack. Thermoregulatory capacity declines with age, sweat response is blunted, and the sensation of thirst weakens. So an older person can be significantly dehydrated without feeling thirsty. Many common medications, including diuretics and several classes of cardiac and psychiatric drugs, interfere with fluid balance or with the sweating response itself. And the perception of heat is less acute, so the internal alarm that would send a younger person looking for cooler air does not go off. Add social isolation, and the picture completes itself. The single strongest protective factor identified in the aftermath of major heat waves has consistently been whether someone checked on the person. Not air conditioning ownership, though that matters enormously. Whether a neighbour, a relative, or a caseworker physically knocked on the door. That is why heat waves produce clusters of deaths discovered days apart rather than a single visible event, and it is why the interventions that work are unglamorous. cooling centres with transportation to reach them, utility shut-off moratoriums during heat emergencies, wellness check programs. None of it looks like emergency response. All of it saves more lives than anything that does. That invisibility is a real problem for public response. A tornado leaves a debris field. A flood leaves a waterline on a wall. A heat wave leaves an elderly person who did not answer the phone. Distributed across a metropolitan area, discovered days apart, attributed to whatever organ failed first, which is precisely why the heat risk framework we mentioned earlier matters operationally. Building a warning scale around observed health outcomes rather than around a temperature that sounds dangerous is an attempt to make an invisible hazard visible before the fact rather than after it. Level 3 and Level 4 days correlate with measurable surges in emergency department utilization, which means hospitals can staff for them. And then there is the night, which is where all of this compounds. Recovery is not optional. The body requires a period each day cool enough to unload accumulated heat, restore fluid balance, and let cardiac output return toward baseline. Sleep is when most of that happens. Remove the cool period and you remove the recovery, and the following day begins with a deficit rather than at zero. That is the significance of record warm overnight lows in the low 80s along the Gulf Coast during this event, and of the warmest average overnight minimum ever recorded across the contiguous United States in July. Those numbers are not a curiosity for statisticians. They are the removal of the mechanism by which people survive the daytime, so bring it back to a single afternoon in South Florida. 99 degrees of air temperature, 110 degrees of heat index, a dew point that has throttled the only cooling channel the body has left, on a day when the wind that normally arrives off the water is not coming, in a city whose overnight low will offer very little. The number that goes into the archive tonight is 99. The number that describes what happened to 800,000 people in Miami-Dade is not in the archive at all. Part 15. The objections and what survives them. Every heat record produces the same handful of objections, reliably, within hours. I want to go through them properly, because dismissing them is both lazy and counterproductive, and because 2 of them contain real points that improve your understanding of the event, rather than undermining it. The first is the urban heat island. Miami International Airport is a paved environment surrounded by runways, taxiways, terminals, and roads. Asphalt absorbs solar radiation efficiently and re-radiates it. Vegetation that would otherwise cool through transpiration has been removed, and the local temperature is genuinely elevated relative to undeveloped land nearby. All of that is true. It is well documented, it is quantified, and it is one of the most studied problems in surface climatology. Station siting standards exist because of it. Homogenization procedures exist to detect and correct for it. By comparing a station's record against its neighbors and looking for the characteristic signature of local development rather than regional change, here is what the objection cannot do. It cannot explain a record for the warmest average overnight minimum temperature across the entire contiguous United States, because that figure is an average across thousands of stations in every conceivable setting, urban and rural, and a national record requires the whole distribution to move. It cannot explain a Gulf of Mexico running 1.8 degrees Celsius above baseline, because there is no pavement in the Gulf of Mexico. It cannot explain a ridge measured at nearly 6,000 geopotential meters, because that measurement comes from weather balloons and satellites sampling the free atmosphere thousands of feet above any parking lot. And it cannot explain 100% coral mortality at a restoration site, because coral is a biological instrument sitting underwater. The signal shows up in datasets that have no pavement anywhere in them. That is what survives the objection. The second is weather modification. The claim that heat domes are engineered, that the ridge overhead was put there deliberately, circulates every single summer, and it will circulate about this one. The response is an energy budget, and I think the energy budget is genuinely interesting rather than merely dismissive. A continental scale ridge represents a redistribution of energy on a scale that is difficult to state in ordinary terms. We are talking about the thermal state of a column of atmosphere spanning much of a continent, sustained across weeks. The total energy involved dwarfs global human energy production by orders of magnitude. There is no technology, deployed or theorized, that directs energy on that scale. The only weather modification actually deployed at scale is cloud seeding, and it is important to be accurate about what it does. Seeding introduces particles into a cloud that is already there and already precipitating, in order to nudge the efficiency of the precipitation process. It does not create clouds, it does not create storms, and it certainly does not build or maintain high-pressure ridges. Its measurable effects are small enough that the scientific literature still argues about how to detect them. I also want to be precise rather than sneering about the adjacent topic, because the sneering version is wrong. Solar radiation management is a genuinely debated proposal. It has been studied seriously by serious institutions. The governance questions around it are real, and reasonable people disagree strongly about whether it should ever be attempted. But a proposal under study is not a deployed system, and nothing operating at present could produce the patterns we are discussing. The third objection concerns the death toll, and what makes it interesting is that it circulates in both directions simultaneously. Some people argue the numbers are inflated, others argue they are being suppressed. That both accusations exist for the same dataset tells you something about how much either is grounded in the methodology. What survives is that the methodological bias runs in one direction only, for the reasons we walked through. Heat is coded as a contributing rather than underlying cause, the confirmation process is slow and conservative, and the in-season numbers are flaws. Nobody has to be lying for the reported figures to be substantially below the true ones. There is a version of the sighting objection that is more sophisticated and deserves its own answer, because thoughtful people raise it. The argument is not that the airport is hot, but that the airport has become hotter over time as the metropolitan area grew around it, and that this growth trend contaminates the long-term record in a way that looks like regional warming. That is a legitimate concern, and it is exactly what homogenization procedures are built to detect. The method is comparative. You take a candidate station and compare its record against a network of surrounding stations, looking for step changes and divergent trends that appear at one location and not at its neighbours. Real regional climate change affects all of them together. Local development affects one of them alone, and it leaves a signature that is statistically distinguishable. More to the point for today, the urban heat island is primarily a nighttime phenomenon. Its strongest expression is in the overnight minimum, because the effect is largely about thermal mass-retaining heat, after sunset rather than about daytime absorption. Its influence on the daytime maximum, which is the number in question for the 1942 record, is considerably weaker. So the objection is least applicable to precisely the measurement being discussed, and there is a simpler check available. The 1942 record was set at a Miami that was a fraction of its present size, with a fraction of its present pavement. If urban development were the dominant driver of the daytime maximum at that station, the record would have been broken repeatedly during the enormous growth of the second half of the 20th century. It was not. The record has stood through the entire construction of modern Miami, which is fairly strong evidence that whatever sets the ceiling on that station's daytime maximum, it is not the parking lot. The fourth objection is the one that uses a real number, and it is the most interesting of them all. If 1942 still holds the record, has anything really changed? Everything we have covered is the answer, but let me put it in one place. The all-time high is a single value from a single afternoon, and single extreme values are the noisiest statistic in any record. Meanwhile, the distribution has moved decisively. The streak record went from 32 days to 46. Daily heat index records fell nearly 3-1 against daily temperature records in 2023. The national overnight minimum record was broken by a margin that is very large for a continental average. Sea surface temperatures are at record daily highs. The Weather Service lowered its warning thresholds for a single county because the old ones no longer described the risk there. And the reason the daytime maximum is the one metric that has not moved is the humidity break. The same rising moisture that is driving every other record is suppressing the number that objection relies on. The record's survival is not evidence against the change, it is a direct consequence of the mechanism doing the changing. The fifth objection is the cleanest to answer. El Nino explains this, therefore climate change does not. Both are true at once, and they are not competing explanations, because they operate on different terms of the same equation. El Nino redistributes heat already stored in the ocean and changes where the atmosphere feels it. The baseline it is redistributing on has shifted upward. The numbers we are reading are the sum. There is a sixth objection I want to raise myself, because nobody else will, and it is the strongest one available. It is possible that today is simply a rare alignment. 3 breaks failing at once is unlikely, and unlikely things happen, and a single occurrence of an unlikely thing is not a trend. If Miami reaches 100 degrees this afternoon, that will be the second occurrence in 130 years, and 2 is barely more of a sample than 1. That objection is correct, and it is the one I would want held against this video a year from now. The way you test it is not by arguing about today. It is by watching whether the odds keep appearing. If a forecaster writes 10% again next August, and again the summer after that, then the distribution has moved. If today turns out to be an isolated alignment that does not recur, then the ceiling was real and it held. I do not know which of those it is, and neither does anyone else. What is documented and what does not depend on how today resolves is that the water is warmer, the nights are warmer, the streaks are longer, and the agency that issues the warnings has already changed its thresholds for this specific county. And notice, finally, that none of these objections actually touch the claim this video is making. I am not making an attribution argument. I am describing a mechanism that has stopped working, and the mechanism can be examined directly, with no reference to what caused the water to warm. Part 16. What happens? When the ocean stops. Start with one station, one thermometer at one airport on one afternoon, 1 degree away from a number, then step back once. It is not one station, it is a coastline, and every city along it operates on the same 3 breaks, powered by the same water, and every one of them has been quietly assuming those breaks would always be there. Step back again, it is not a coastline, it is an ocean basin running 1.8 degrees Celsius above its baseline, holding a quantity of energy that will not dissipate this year or next, connected to a Pacific that has reorganized itself and has not finished doing so. Step back one final time. It is a planetary heat budget, and everything we have discussed today is a local expression of where that budget is currently being stored and how it is being moved around. The energy did not come from nowhere, and it is not going anywhere quickly. Here is the central point of everything we have covered in its final form. Miami has spent 130 years being protected by the water around it, and every one of those protections was a loan taken out against a temperature difference. Humidity works because the ocean is warm enough to evaporate, but the air can still absorb what it produces. The sea breeze works because the land is warmer than the water in the afternoon. The storms work because the sea breezes have enough strength to collide with force. All 3 of those depend on a gradient, and gradients close from both ends. That is what makes coastal subtropical cities a different kind of climate risk than anywhere else, and it is not the risk anyone talks about. The conversation about coastal climate is almost entirely about sea level, and sea level is a real and serious problem. But the mechanism that is failing today has nothing to do with how high the water is. It has to do with how warm it is, and what that does to a city's ability to cool itself every afternoon. We have always believed that the ocean is what makes a coastal city livable. But what if the ocean is also the thing that decides when it stops being livable? And what if that decision looks less like a flood and more like a Tuesday afternoon when the wind does not arrive? That distinction matters for how these records will behave from here. When a forcing increases gradually, records creep. Each year is a little warmer than the last, and the archive fills in smoothly. But when a suppression mechanism is removed, records do not creep. They jump, because a ceiling that was holding the distribution down is simply gone, and the values that were always physically possible underneath it become accessible all at once. Miami's record has not crept for 84 years. It has sat there, untouched, while everything around it moved. That is the signature of a ceiling, not of a slow climb, and ceilings do not degrade gracefully. The coral is the longest-running instrument in this story, and it is worth ending the physical argument there. Reef-building corals have been laying down structure in Florida waters for thousands of years, and their skeletons contain a chemical record of the water they grew in. They are a thermometer with a very long memory and no dependence on anything humans built. In 2023, a restoration site off South Florida recorded total mortality. The instrument did not report a warm year. It stopped. There is a reason I keep returning to the word protection rather than the word warming, and it is because the two produce completely different risk profiles for planning purposes. If you are managing a city whose temperature is warming gradually, you can plan against a trend. You build codes around the projected distribution, you extend the cooling season, you upgrade the grid in increments, and the changes arrive at roughly the rate your budget cycle can absorb. If you are managing a city whose temperature has been held down by a mechanism, the planning problem is completely different, because the mechanism does not degrade smoothly. It works, and then on a specific afternoon under a specific pattern, it does not. Everything downstream of it, the emergency response staffing, the grid load, the hospital capacity, the assumptions built into building codes about how hot an unconditioned interior can get, was calibrated against a distribution that assumed the mechanism was there. South Florida's infrastructure has been built and permitted and insured against a climate in which the official record high is 100 degrees and has been touched once. Not because anyone made that assumption deliberately, but because that is the record everything references. The design values, the historical extremes tables, the engineering standards that specify what a system must tolerate, all of them come from an archive that was shaped by 3 breaks nobody wrote down. So here is what I would actually watch in order. Today, watch whether the official Miami station reaches 100 degrees, and specifically watch the daily climatological report that the Weather Service office in Miami issues each evening. That product, not a forecast and not a news story, is the document that settles it. And note the timing, because it matters. The next weather forecast expects a pattern change later this week that lets afternoon thunderstorms return, including along the coast, which would bring the 3rd break back online and end the run. That makes this afternoon the best and possibly the only shot the atmosphere gets. Over the next month, watch where this ridge finishes against the record for monthly high-pressure intensity. Forecasters flagged it as record-threatening while it was happening. The verification, the actual measured heights against the historical record, will not be published until well after the pattern breaks, and it is the number that will determine whether August of 2026 is remembered as a hot month or as a structural outlier. Over the following months, watch how much of Maricopa County's backlog converts. 63 confirmed against 558 under investigation. That conversion rate is the number that reveals the true human cost of this summer, and nobody will know it until long after the weather has been forgotten. Consider what that means in practice for a single building. An engineer designing a cooling system sizes it against a design day, typically a temperature that historical records suggest will be exceeded only a small percentage of hours in a year. If the historical distribution that produced that design day was shaped by a sea breeze that arrived every afternoon, then the system was sized against a climate that included the sea breeze. Remove it, and the system is undersized, and it will be undersized on precisely the days when it matters most, when the entire metropolitan area is demanding maximum output from a grid designed against the same assumptions. That is the failure mode worth worrying about in a place like South Florida, and it is not heat stroke on a beach. It is a peak load event on an afternoon when the wind did not come, in a region where the loss of mechanical cooling is not an inconvenience, but a medical emergency for a substantial fraction of the population. The record from 1942 was never a measurement of how hot Miami can get. It was a measurement of how much protection the ocean around it was willing to provide on the worst afternoon anyone had ever seen. For 84 years that answer held steady, and the record held with it. The answer has changed, and the record is now sitting inside forecast uncertainty on an ordinary Tuesday in August. And the thing I cannot stop turning over is the timing. Everything in this story. The 99 degrees, the record ridge, the 80 million people under alerts, the warmest night the country has ever averaged. All of it happened on the leading edge of an El Nino that NOAA gives 90% odds of reaching strong or very strong status over the next 3 months. None of this happened at the peak. So the question I would carry out of today is a specific one, and it has a specific answer date. What does the Nino 3.4 index read when the September update lands?